Hi, my name is Lawrence Perkins, and welcome to Sensors Part 1. This module will be a continuation of the introduction to Arduino module we finished, where we learned to interact with the Arduino and all of its peripherals. And then we learned how to code in its environment by making an LED turn on and off, like we have our little onboard pin 13 doing right now. So in Sensor Modules Part 1, we'll be going over how to represent data using our LED visual display, LEDs and resistors. So we don't have to always be plugged into the serial console to know what the microcontroller is doing. We'll then be looking at the differences between analog and digital signals and how the Arduino is able to handle both. And then from there, we're going to start building our balloon shield, which is going to allow our sensors, like this temperature sensor here, to interface with our Arduino without using a breadboard. It allows it to secure a lot more firmly to whatever we're attaching to. And then after that, we're just going to start integrating our sensors, beginning with our internal temperature sensor, our thermometer. So let's get started with our visual display. For this one, we'll be using our breadboard, our LEDs, resistors, and some wires. So we'll go ahead and grab all those and continue when ready. I'm just going to unplug that so I don't short that out. So first, what is a breadboard? Well, a breadboard is a piece of equipment that we can use to prototype our circuits. When I say that, prototype, we can install and uninstall components easily on this platform, and we're able to connect it to boards externally as well. The benefits of using a breadboard is that it's easier to replace components if they are not working. It's a nice test bed to actually test components to see if they're working or not before we replace them, before we actually install them permanently on a shield. So how is everything connected in here? Well, we have columns and rows, and basically inside of these uncolored gridded pins, we have columns that are all connected to each other. And by that, I mean this first column here, column 1, A through E, are all connected to each other, but not 2A through E. So each column of 5 rows are connected to each other, but they're not connected over here. So column 1A through E are connected, but column 1F through J are not. And then we also have our power rails. We have our negative, and positive. These have all of the rows connected. So 1, 2, 3, 4, 5, and then we have all those, and then our positive is connected here. The negative is not connected to the positive. Same thing down here. The only difference is the negative and this negative are not connected. Same with the positive and positive. So these are basically 4 different rails that are able to connect. And actually, I have a breadboard that is same thing. It's just been disassembled. It's a lot older, so it had an adhesive back. On the back side, you can see a good representation of what's going on underneath the pins. So I just pulled out this little metal connector, and you can see it just basically pinches whatever lead you have going into the breadboard. And then above that are just those five holes that you can insert LEDs or whatever sensors into. So these just sit in like that, and they're arranged into columns that are all connected to each other, and then our power rails that are all connected in common. So pretty cool. Alrighty. So for documentation purposes, breadboards are actually laid out in a grid. So you heard me mentioning 1A, 1B, a row of 1. So we have our rows labeled here and here, and then we have our columns labeled here and here. It's just to make it easier to actually document and write down how you have everything connected, so you don't have to go tracing wires, which is time-consuming and tedious. So let's start building on our breadboard by adding our LED that we had connected to pin 13. We're going to be adding it and a resistor to test externally. So first, we're going to connect the negative lead of the LED to C10 or close to C10. These coordinates are just to make it easier for you to know how everything's connected. But if you see me connecting it to D10, then it still works okay. It's just because I'm off by a column, so it's not really super critical. But we're going to connect the negative lead of the LED to C10 and the positive lead to C11, like in the diagram. And then we're going to connect our 300 ohm resistor, which is this resistor with the band orange, orange, brown, which is 33 and 10, so 330 ohms, to the positive lead at D11, and then across the channel to F12. So that'll allow us to stay in the same row, but not basically connect those two together, except they have to go through the resistor. And then we're going to connect the breadboard wire to the negative lead 10, D10, to the ground rail. And then after that, we're going to connect our rails up. So we have J11 to pin 9. And then we have our ground rail, which is the blue rail here, to our Arduino. So I'm just going to flip the board around and try to stay somewhat similar. So remember our negative, I'm actually just going to go back. Whoops, not that far. To C10. And the negative is the flat side on the LED, which happens to be the short pin. So our negative is going to C10. So we have our C, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C10, and then our positive is C11. So we're just going to connect just like that. Cool. And we're going to take our resistor, and I like to bend these kind of using either your fingernail, or you can use something with not a sharp point, but something that's kind of rounded to just bend the lead as close as you can to a rounded 90. So it should look something like that. That'll make it easier to use later. But this one is going from D11 to F11. So our 11s and our D to F. All right, and there's no polarity, so you can hook this up any way you want. And then we're going to take a negative lead. Let me get my leads ready. And sure, we'll use this one. Our negative, in particular the D10, but I'm just going to connect it down here to our negative rail. Any of these, so they're all connected, like so. And then after that, we're going to bring our Arduino in and connect J11, which is the other side of the resistor. So just J11, and that's going to go to pin 9 on the Arduino. We see 13, 12, 11, 10, 9. All right. And then we're going to connect our ground rail anywhere on the rail to our Arduino's ground, which is right next to pin 13. Cool. So we're going to use the same sketch, plugging our Arduino in. We're going to upload the same sketch, but we're going to change one thing. Let me actually show my sketch. All right, remember how we defined our LED as being on pin 13 in this variable? Well, we're going to change that from 13 to a 9, and that'll tell the Arduino we want to execute the same code, but only using pin 9. So we're going to verify and then upload to our Arduino. And then we should see something happen. Cool. So we have everything wired up okay. Our yellow LED is nice and happy with our current limiting resistor in series. It's not quite as bright and it'll last a lot longer. So cool. Have a minute to actually tinker with the delay times if you want, and then we'll continue building our visual display on the next slide. So we're basically just going to duplicate this circuit 3 more times to the right. And what I mean by that is the positives on the right or the left, and then the negatives on the right. Just duplicating that circuit. And then we're going to connect all of the negative leads to the ground rail. And then the positive rails are going to be tied before the resistor. And then there's another picture showing everything. And then after that, we're just going to tie this one rail here to all the other LEDs via resistor. So we'll just start building that here. Lost my red LED. All right, red next. So again, the negative side is the flat side, and the negative is on the right, my right. And first, we're going to go ahead and unplug our Arduinos. Next one is blue. Next one is green. I'm actually out of green, so I'm going to use this orange. Whoop, as I completely bend that lead. That's okay. That's better. And then we're just going to take our resistors. I bent a few beforehand. And go from E to F or D to F. Remembering it doesn't matter so long as they're on the same row. Awesome. So now all they need are their positive rails tied together. So green here to this rail. We have our blue. Why not use a blue? To this rail. It's going to start looking really jumbled, but it allows us to test everything before we get it permanently installed. Then our red is going to get power from the same spot as our yellow. All right, so once our positives going to our resistors are all tied together to our pin 9, we're just going to connect all the negatives or the grounds together, going to the ground rail. So this one already has it. There we go. One more. All right. So once you have everything hooked up, we'll go ahead and plug it in. And we have all but one blinking. So let's see if I missed a ground. What did I miss here? Let's see if you can see what I did wrong there. If you said installed the LED backwards, you're 100% correct. So we'll just flip that around, making sure the flat side is pointed to the negative. And there we have it. All right. Cool. So now we know our visual display LEDs are working. So let's go ahead. Well, we already did that. Go ahead and tinker around about if you want, and then we'll continue. But let's think about how we want to, or what we're going to do to actually get these to blink individually. Because remember, we want to use this to represent data instead of using the serial console. So one would be one lit, two would be two lit, etc. It's just another way to represent data. So what we can do is we can actually just remove the wires connecting the resistors together, the inputs to the resistors together, and connect them all individually to different pins. So right now we're using pin 9 for our yellow LED, and then we want to connect our red LED's resistor to pin 7, the purple LED's resistor to pin 6, and the green LED's resistor to pin 5. So let's go ahead and talk about what that looks like in code. In code, we would actually just change or add the we'd add pin mode. So we'd get rid of the integer that we were using to store the LED's pin number, and then just represent that via integers moving forward. But first, let's go ahead and make these changes. So I'm just going to unplug the Arduino. We have the input of our red, the input of our blue, and the input of our green, which in my case is orange. So now I have the inputs going to the from the resistors. So our red LED is going to go to pin 7. Our blue LED is going to go to pin 6. And then our green LED is going to go to pin 5. So that's what it would look like in hardware. So now if we were to plug it back in, we should only have our yellow LED blinking, which we do. So we need to tell the Arduino how we have those connected. So in the sketch, like I mentioned before, we just tell it what pin modes, or tell it what pins they're attached to, and we want those pins assigned as outputs. After that, we want to modify our sketch to turn the pins all off at the beginning of the loop, just like we did in our original, and then turn them all on, but put delays in between so we know that they're turning on one at a time. If we have them all turn on at once, we wouldn't know if there was something wrong, if they got connected together somehow. And then after that, we'll just compile and upload our code. So first, I'm going to just go up to our pin modes. I'm going to comment this out, remembering it's the 2 forward slashes. Come down here to our pin mode, and I'm actually going to copy this line 3 times. This is our, well, that is our green LED. I was about to call it our orange, but yeah. Blue in my case here. Actually, I'm totally, no, I'm going to call that green. Indecisive today I am. Red, and then our yellow. Typing. And then instead of LED, pin 5 for our green, 6 for our blue, purple, if you have purple in there, 7, and then pin 9. And then on our next slide, we just have these digital rights reversed, so we're just going to switch this to low, update our comment, and then call that 5. So all I'm doing here is I'm just going to duplicate that. Nine. All right, and then we have a delay. And after that, we're going to start turning them on or high, updating our comment, one at a time with a half a second delay, which is 500 milliseconds. So I'm just going to copy this line 3 times. Instead of LED, we're going to go 5, 6, 7, and 9. And then for a comment, I'm just going to note that that's green's on, blue in my case, or purple, red, and then yellow. Cool. So once you have all those changes in, we're going to go ahead and compile and then upload our code to the Arduino. Compiling here. Sweet, we are error-free, and then we're going to go ahead and plug our Arduino in first. Should still have that one blinking, and then upload. Oops, and I totally typed a 4 in when I was reaching for that. All right. So now that we can see, it's turning on orange, blue, red, and then yellow, and then waiting 1 second after turning everything off. So it looks like everything's wired up correctly, and we're actually using our LED display. And right now it's representing weights and time, but we can actually use this to represent different types of data, which we'll get into. So to reemphasize, you should see the green LED turn on, then the purple or blue, then the red, and then the yellow. If you want to, go ahead and tinker around with this. See if you can make the little Knight Rider pattern go back and forth. That's always a fun one to see. And then when you're ready, we'll just continue. All right. So if you remember from our Arduino part 1, we went over, our Arduino introduction to Arduino. We went over our different methods that we have available to use in the Arduino. To start our serial line so we can communicate with our computer and other devices would be using serial begin. And then we normally find that in the setup loop because it only runs once. Our next statement would be serial print, and that's to actually print data out to that serial line, print and print line, remembering that print only prints and then continues to print on that line until you call something like print line. So those are both found in void loop, although you can have them in void setup. Say you're initializing an I2C bus, it would be useful to have these inside of setup as well, but they're generally found inside of our loops. And then pin mode is a setup, so we find that up in void setup. That's where we're actually assigning our pins and telling Arduino what it does. And then we have our digital write, which is when we actually write out a state to a pin. And that's generally found in void loop. That's what we're using to actually turn the LEDs on and off again. Our delay time can be found anywhere, but it's generally found inside of loop again. And that's just telling the Arduino, I want you to sit there and do nothing for X amount of milliseconds. So cool. That is our LED visual display built and ready to use once we actually just go through talking about the differences between analog and digital signals and how the Arduino is able to use both. So a good representation of the analog versus digital in your everyday life would be an analog clock versus a digital clock. They both do the same thing. They both represent time. They just represent it differently. On your analog clock, you generally have a second hand that either clicks in seconds or it just slowly rotates around the clock. And then your digital clock, you may have a second counter or a millisecond counter. If you have a really good digital clock, you can go microseconds, nanoseconds, etc. But it has a finite resolution, whereas your analog clock doesn't just jump from one space in time, second hand being over the 2, to the second hand being over the 3. There's time in between there versus the digital. So we can actually think about this in the electronic world as voltages. So voltages are continuous constantly. So they vary constantly, and your time difference, for each time difference, there's generally a difference in voltage, and that time difference can be anything. So there's infinite states inside of your analog signal, and it continues over time. Your digital signal has two states. It's either on or off, and the on is whatever the high is on the bus, in the Arduino's case 5 volts, or off being 0, which is 0 volts on your bus. So digital data has to represent, digital signals have to represent data in an encoded signal, like this example here, which is an arbitrary just 8-bit signal. So we have a start bit, which is low. That's 1 bit in time. And then we have 6 or 7 bits of data followed by a parity bit, which is the 8th bit. And then our end of that piece of information is called stop bits. And that can represent anything inside an 8-bit. Well, it can actually represent anything. But as far as this signal goes, it just has bit 0 being high, bit 1 and 2 being low, bit 3 being high, bit 4 low, etc. So that's how we're able to represent different numbers. So the Arduino is able to read analog signals using a built-in ADC, which takes care of all of the hard stuff. And it's integrated right into this chip here. Nothing at all that we need to do other than simple code to initialize it at the beginning of our setup loop. So when it converts an analog to digital signal, it needs to represent it in digital format. So either a single bit or a series of bits that are set high and low. So in this example, we have an example of a low resolution conversion, which is 1 bit in length, which has 2 states, a 0 and a 1. So you can see when that voltage waveform is high, we have our bit 1 being set to high. And then when it's low-ish, it's being set to low. And that doesn't really give us a lot of information other than the voltage is rising and lowering and rising. But it doesn't give us an accurate picture. So we would need more bits for a higher resolution to get a better idea of what's going on here. So we can just add 3 more bits to get a 4-bit signal that'll give us 16 states. As you can see by the green line, that actually gives us a better idea of what's going on here. It's like, so it's rising and then kind of tapering off and then going back down. So again, it's a digital representation of what we see in the analog world. And the Arduino takes care of all of this. So how do you determine how many bits to use? If you want to tell that there is voltage on the line, 1 bit would be sufficient, but it doesn't tell you how much voltage. That would be taken care of with more bits. So the question is, what do you need to know? In this example, we have 3 different resolutions, and we want to know if something is there or if it's a circle. If we want to know if something's there, then 10 dots per inch would absolutely tell us that something is there, but it doesn't necessarily tell us that it's a circle. It can be a number of shapes. We start increasing resolution, and then we get a better idea at 72 dots per inch that it's probably a circle. And then once we reach 300 dots per inch, we are pretty confident that it is a circle. So a real-world level of precision example would be finding out what information we would need to know if we wanted to hit the barn with a rock that's 10 feet away. So what do we need to know? We need to know where the barn is. So we can think about it in the idea of bits, in that we can actually have the barn being represented as a 1 and not the barn being represented as 0. So 1 means hitting the barn and 0 means missing the barn. That's 2 states. Well, as you can see in the upper left-hand corner of the 1 bit, there's the possibility of you not hitting the barn, even though it is inside the 1-bit rectangle, if you will. So how can we get more accurate on this? Well, we can just add more bits. Now we have 2 bits in 4 different states. And that gives us a better idea of what part of the barn is hit, right? So we can just keep doing this. Here's 4 bits, 16 states. Just keep adding resolution until we get a pretty good idea of where the barn is, right? So what's the downside of doing this? Well, it costs more in terms of memory on your hardware, the storage to actually store the number since there's more bits, and also the speed, your bandwidth of whatever you're trying to move that signal across. There's also a monetary cost. Hardware that is able to store a lot of bits generally cost more. So if you wanted a 1,000-bit ADC, you're not going to find that anywhere near the price range of an Arduino. So for an Arduino, 10 bits is the sweet spot. So it depends on what you're trying to see. So it turns out with the Arduino, 10 bits is a pretty sweet spot and get 1024 states. So just keeping in mind, more bits gives you more precision, gives you more states over any voltage range. Because remember, the analog to digital converter is just reading in a voltage via the analog in pins and representing it in an integer as a state of that pin. If you need more precision, you just simply increase bits, but that would be a hardware change. That's not something you would do on your Arduino again because it's a 10-bit ADC. So inside the data world, here's a fun fact. There's 8 bits in a byte. So how many bytes is 10 bits? The answer to that would be 1.25 bytes. So the ADC stores its values in 1.25 bytes of memory. So, converting a 10-bit, 10 bits has 1024 possible values between 0 and 1023. That would give you a resolution in voltage of about 48.9 millivolts, or 0.00489, represented by that nice mathematical quality there. Which means it's pretty precise. It's more precise than what we really need to measure temperatures and pressures. So it has a lot of room to expand upon, depending on what experiments you're doing. All right. So a real-world example of how the Arduino would measure, let's say, the temperature in a desert at 42 degrees Celsius would be to take the temperature and measure it via a sensor, which has the ability to read from 0 degrees Celsius, which would be represented by 0 volts, or 50 degrees Celsius, which is represented by 5 volts. That sensor then sends its data, its voltage, when it's 42 degrees outside, as 4.2 volts. That 4.2 volts is read in by the 10-bit ADC in the Arduino, and then it, which has a resolution between 0 and 1023, representing 0 to 5 volts, it then takes that 4.2 volts and spits out a number, which would happen to be 860, representing that 4.2 volts inside of the digital world. So taking the analog signal and representing it as digital data. So the math that it uses to do that is simply 4.2 divided by the 5 volts times the number, the maximum state number, which is 1023, which would get you 860 and change. It just rounds to the nearest state internally. So it's doing that several hundred times per second, whatever the refresh rate is of the ADC. And then you're able to plug that into anything you want to compute values inside your Arduino. But ultimately, it's going to store that number in binary, which are the bits, which that's what it looks like. And it's going to plug that into a data logger, which is our open logger. So it's just a nice real-world flowchart of what our system is going to be doing once we build it. So it all seems really complicated and really confusing. Really, it just takes time and experience to get used to working with data in this manner. But just remembering that the Arduino takes care of a lot of the heavy lifting on the fly when we want to read a voltage from any of these analog inputs. So just working with it and continuing to get used to it is all it takes. So in this next part, we're going to actually practice using our analog inputs and manipulating data physically using what's called a potentiometer. So once you're ready, we'll go ahead and start with that in a moment.